Okay, good people. Thank you all for being here. I want to begin today with a little bit of a caveat or a warning that the audio might be a bit off, the video might be a bit off. I'm not working from my normal computer because the network adapter on my work computer decided to die overnight. So I've got a kind of jury-rigged setup today, but thankfully you guys are not the first class of the day, you are the second. So I've been able to work most of the bugs out. But yeah, if you notice things looking a little different or sounding a little different, that's why. But you know, with that out of the way, let's get to it. I think the .cam software should be working well. Can everybody hear me okay? Any problems with feedback or loud noises? Anything like that? Excellent. Okay. Glad to hear it. Thank you, Sergio. So, this is, of course, Calc 2, Section 2. Today, as far as I'm aware, is the 7th of October. And we're doing something that might be a little bit scary today. We're beginning the part of this class that makes this class hard. Right? I recognize that what we've done so far is not exactly easy, but that stuff is not the reason this class has the reputation it does. The reason Calc 2 has the reputation it has is because of the middle third of this course, which is on convergence. So today we're going to begin the convergence part of the course. And the word converge can mean different things depending on who you are and what you're doing. If you're a fan of 90s hardcore punk, then Converge is of course a band. If you are a poet, then converge can mean like to come together, as in two roads diverged in a yellow wood. Converge being the opposite of diverge there. But if you're a mathematician, then converge or convergence usually means, so broadly speaking, to converge means some infinite process yielding a finite result. And we are going to end up with something like 4 different notions or concepts or definitions of convergence. I'm going to start with one that has to do with a certain type of integral, because we've spent the whole semester so far talking about integrals. It's the easiest way to introduce this. But then over the next few weeks, I'm going to introduce objects called sequences, and then objects called series, and then objects called power series. And each one of these things, integrals, sequences, series, and power series, have their own notions of convergence. So today we're going to learn what it means for a certain kind of integral to converge. You want to be hyper organized in your notes from now on. And if you're the sort of person who has a somewhat hard time managing your time, finding time to study, stuff like that, then you want to take very seriously the next 6 weeks. It's going to be hard. You're going to need to put in a lot of time. And my suggestion is to study every day after class. I'm glad to hear that. So the first notion of convergence is going to come from section 7.8, which is the section we're beginning today, and the section from which this week's homework will come. The section is titled Improper Integrals. So, if you remember way back in section 5.1, towards the end of your Calc 1 class, you guys defined the integral. You defined the definite integral, and you used Riemann sums to do so. The first step in defining the integral from a to b of f of x is to take the interval ab and chop it up into n different pieces of finite length. With improper integrals, for one reason or another, it's not possible to form a Riemann sum. So the integrals in section 7.8 are called improper because the area these integrals measure is that of a region which is either infinite in length or infinite in height. That's the basic idea. All right, so we know that integrals measure area, the area under f of x from a to b. The integrals we're going to look at in this section, that region whose area you're measuring is either infinitely long or infinitely tall. If the region is infinitely long, we call this a type 1 improper integral. If the region is infinite in height, I know this is very clever. Mathematicians are not very cute when we name things. This is called a type 2 improper integral. All right. I'm going to show you today how to deal with type 1 and type 2 improper integrals. And I'm going to try to discuss with you a little bit why they need to be dealt with in that special way. The crux of it is what I said a second ago. You can't form Riemann sums for either of these. And unfortunately, it is the Riemann sum that we use to define the definite integral. And the Riemann sum that allows us to have, for example, a fundamental theorem of calculus. And we use FTC2 every single time we integrate, right? It's FTC2, the fundamental theorem of calculus, version 2, that says you can do a definite integral by finding an antiderivative. Well, if we don't have that, then we're pretty well and truly fucked. So instead of abandoning the fundamental theorem of calculus altogether, we're going to kind of find a way to hack these integrals and apply the fundamental theorem to the hacked integral, and then do something to that in order to get the value of the full improper integral out. So real quick, type 1 integrals, which are integrals where the region is infinite in length, these will look like integral a to infinity of f of x dx, or integral from negative infinity to a of f of x dx, something like that. Get this out of the way. Type 2 improper integrals, they don't look weird at all. These are like integrals. I'm going to use a to c f of x dx, or integral c to a f of x dx. But here, f of x has an infinite discontinuity, i.e. vertical asymptote at x equals c. Okay, so your type 1 integrals, if an integral is improper and it can be classified as a type 1 integral, that means that the region is infinitely wide, which means that you have to integrate like from some number out to plus infinity, or from negative infinity up to some number, or maybe from negative infinity all the way to plus infinity. You can have both happen at once, but I'm not going to address that today. We'll address that on Friday. Type 2 improper integrals, when you first write them down, they don't look weird at all. They just look like regular definite integrals. The issue, rather than coming from the bounds here, comes from the fact that the function blows up to infinity at one of the bounds. And again, it's possible that the function blows up to infinity somewhere in between them, but I'll deal with that on Friday. So these are the kind of simplest possible cases for improper integrals, and these are the cases that we're going to address today. Anybody need a second to write the stuff down? Okay, I'll leave it here for just a second longer. When we get into this in just a second, I'm going to show you first how to deal with type 1 integrals. And I want to make a quick comment that type 1 integrals are more important than type 2 integrals. And call me biased, whatever. It's just the truth. Because down the road, when we start dealing with sequences and series, type 1 integrals will come back up again. They will turn out to be important in that study as well, whereas type 2 integrals, we'll only see them in this section. Well, both are important, of course, but type 1 integrals are more important. Okay, I'll refresh my coffee. I'll give you just a second longer to write, but then I am going to move on. Okay. So improper integrals are either type 1 or type 2. If they're infinite in length, we call them type 1. If they're infinite in height, we call them type 2. And they look like this, or like this. I'm going to draw for you a picture, kind of to help us see what the hell we do with type 1 integrals. So this is for type 1 stuff. I have some function f of x like this, and I want to compute the integral from a all the way out to infinity. So my goal is to compute the type 1 integral, or at least define the type 1 integral, a to infinity f of x dx. That means I want the area underneath f of x from a all the way out to plus infinity. Normally, we would do this by building a Riemann sum, right? Normally, the way I would define any integral is through a Riemann sum, but I can't. form the Riemann sum for this integral, because remember, the first step in forming a Riemann sum is to take the interval a, b, and to chop it up into finitely many pieces of finite length. Well, if you take the interval from a to infinity and you chop it up, one of two things must be true. If you have finitely many pieces, then one of them, or maybe more, but at least one of them has to be infinite in length. Otherwise, you can't cover the infinitely long interval from a to infinity. Or if you insist that every piece be of finite length, then you can't possibly cover that whole interval with finitely many of them. So if you use finite-sized pieces, you need infinitely many of them, or if you insist on having finitely many pieces, they need to be infinitely long. The way I usually say this is because delta x, which we usually define to be b minus a over n, would be infinity minus a over n would be infinity, is not finite. This is a problem because it means every single term in my Riemann sum would be multiplied by infinity, and that we know is no good. Infinity times any finite thing is infinity. So we would be in real trouble there. So can't form a Riemann sum, which means whoop, fundamental theorem of calculus is out the window, which means U sub is out the window, IBP is out the window, trig sub, all of it doesn't work. That is disappointing, of course, because those are the methods that we've worked so hard to establish in the first 4 or 5 weeks of this term.
So will those methods come back since we just learned them, or are they just kind of done for at this point?
I assure you, we will resurrect them. We will resurrect them today. So basically, we need to think of a way around this problem. One way to get around this problem was discovered by Henri Lebesgue, a French mathematician, in 1901. And he said, oh, hold on for a minute, nobody told me I need to use vertical rectangles for my Riemann sum. What if I came in here and used horizontal rectangles instead? And I stacked a bunch of those. Believe it or not, this gets you around the issue entirely. But it requires development of something called measure theory. And measure theory is usually put off till graduate school. It's a little bit complicated. So that's not going to be our approach. So one way around this is by dealing with these, instead of using Riemann integrals, we use Lebesgue integrals. Another way around this is to say, okay, I want the area out to infinity, but what if I stop right here? I pick some number r, and I calculate just the integral out to r. So I say, okay, instead of doing the integral from a to infinity, I'm going to do the integral from a to r. That is a Riemann integral. Here, as long as r is a finite number, I can chop this interval up, form a Riemann sum, which means I've got my fundamental theorem of calculus, I can do trig sub, I can do IBP, I can do all the shit I want to do. Hooray! Good news. So instead, we work with this guy. Then send r to infinity. Okay, that's how we do this. So you find a formula for the integral a to r f of x dx. On that integral, you can use your fundamental theorem of calculus, your U sub, your trig sub, all of it. Then once you have that formula, you can take the limit as r goes to infinity. In other words, we define the integral from a to infinity of f of x dx to be the limit as r goes to infinity, integral a to r. f of x dx. Then we work from the inside out. And if it was the integral from negative infinity to a, we do the same sort of thing. If this was integral negative infinity up to some number a, f of x dx, I would define that as the limit as r goes to negative infinity, integral r to a, f of x dx. So this is our shortcut. Solomon, we are talking about improper integrals today. You will want to rewatch the first 30 minutes. It's important. Basically, we're trying to figure out how to integrate functions instead of from like 5 to 7 or 0 to pi, from like 1 to infinity or negative infinity to 0. We're trying to figure out how to do integrals where the region is either infinitely long, which is what we're talking about right now, or infinitely tall, which we'll talk about later. And the trick is to, instead of integrating all the way out to infinity and trying to do anything there, because those are not Riemann integrals, we can't form Riemann sums, we don't have a fundamental theorem of calculus for those, we treat those infinite integrals as limits of finite integrals. Then on these finite integrals, we can use all of our tricks. So you find a formula for this guy, then send r to infinity. Or if you're going from negative infinity to a, you do the same shit, but you take the limit as r goes to negative infinity. All right, so that's the upshot. In addition to learning how to compute these, we're going to develop a bunch of theorems to try and tell us when the result is finite and when the result isn't finite. And that, it turns out, is going to be the hard part, and that, it turns out, is going to be where we start connecting to sequences and series down the road. So today's not too bad. We're just getting used to the concepts. So for example, I may want to integrate from 1 to infinity the function 1 over x squared dx. And the way I would do this is by first setting it up as the limit as r goes to plus infinity of the integral from 1 to r of 1 over x squared dx. So your first step on all of these problems is to rewrite the improper integral as a limit of proper integrals. And now on this proper integral, I can do all the stuff that we've learned over the last few weeks. So this one is not hard. That's lim r to infinity, integral 1 to r, x to the negative 2 dx. You apply your power rule, and you get lim r to infinity, negative x to the negative 1, or negative 1 over x. And that's evaluated from 1 to r. So now if we plug in our bounds, we can take the limit. At the upper bound here, you get negative 1 over r, minus my lower bound, I get minus negative 1 over 1, which is negative 1. What does negative 1 over r do as r goes to infinity? It's like negative 1 over infinity. What is that?
It gets smaller and smaller.
And where does it approach as r approaches infinity? It gets smaller and smaller, getting closer and closer to what?
0.
Good. Yeah, 1 over infinity, that's 0. So this is negative 0 plus 1, or just 1. And so remember, we said that the word converge means an infinite process leading to a finite result. Here, this was certainly an infinite process, and the result was finite. So we will say the type 1 improper integral integral 1 to infinity 1 over x squared dx converges. The adjective form of the word converge is convergent. So you could say that the integral converges, that's a verb. The integral did something. What did it do? It converged. Or you could say that the integral is convergent. That's the adjective form of that word. And its value is 1. Okay. The opposite of the word converge is diverge. So if the limit, let me state this here because I don't think I said it on the previous page. If lim r to infinity integral a to r f of x dx exists and is finite, then we say that the integral a to infinity f of x dx converges or is convergent. If the limit, this limit, does not exist, or is not finite, then we say that the integral from a to infinity f of x dx diverges, or is divergent. So that's how we use the language. And what you'll find as we move forwards through this middle part of the course is that the language is more important than the calculations. We'll certainly be doing lots of calculations, but oftentimes we won't be able to find the value of the object we're fucking with. Right? And mostly here in section 7.8, we will be able to find the value of the integrals, but there will be plenty of problems where we can't. And certainly when we start talking about series, most of the time we will not be able to find the value. But we will be able to tell you whether the thing converges or diverges, and that will become the larger issue. So we take a big step away from calculation in this part of the course and towards proof writing, where we're proving that the integral or series or whatever converges, or proving that the integral, series, or whatever diverges. And we don't care so much about the calculation. So you need to start writing words with these problems. You may notice I write a lot of words as I solve these math problems, and you will need to start doing that as well. You should write in full sentences, correct grammar, be patient, take your time, and make sure you understand what all the words mean and that you're using them correctly. So is there any question about the language that we used here or the result that we got on that example? Sure. So remember, converging means that an infinite process leads to a finite result, and diverging is just the opposite of converging. So we want to say whether or not this integral right here converges or diverges. Since I re-express this integral as a limit of a finite object, I'm talking about dealing with this infinite process. Since this infinite process led to this finite result, I say that the integral converges. Oh shit, why did this motherfucker? Sorry, today is the day from hell tech-wise. So if the limit defining the integral exists and is finite, then we say that the integral converges. If the limit defining the integral either fails to exist or is not finite, then we say that the integral diverges. That is the language that we use here. So if the limit defining the improper integral, meaning the limit of the integral from a to r f of x dx, which is the limit that defines this type 1 improper integral, exists and is finite, then we say that that improper integral converges. If the limit does not exist or is not finite, then we say that the improper integral diverges. So in the example we did here, the integral from 1 to infinity, 1 over x squared dx, converges, because the limit that defines that integral does exist and is finite. That limit is 1. Let's look at another example. Here is another type 1 improper integral. It's type 1 because the region whose area is being measured here is infinite in length. All right, I'm going from 0 all the way out to infinity. I begin by writing it as a limit, and the limit as r goes to plus infinity of integral 0 to r x over x squared plus 1 dx. And now this integral right here is not improper. It's a regular Riemann integral. So I can use my fundamental theorem of calculus. I can use U sub, trig sub, IBP, all the stuff I want to use. What should I use for that integral? How would I evaluate the integral of x over x squared plus 1 on any other day?
U sub?
Yeah, good, U sub. What's the substitution?
X squared plus 1.
Good. So I'll let z be x squared plus 1. That means dz is 2x dx. And I also need to change my bounds. My bounds right now are x equals 0 up to x equals r. When x is equal to 0, z is equal to 0 squared plus 1, that's 1. When x is equal to r, z is equal to r squared plus 1. My new bounds will be 1 to r squared plus 1. And my integral will be limit r to infinity, that's still there. Very important you don't forget to write these limits. All right, if you forget to write these limits, or if you get lazy, sloppy, and stop writing these as limits, I have to take points off. Integral r to infinity, or sorry, limit r to infinity, integral 1 to 1 plus r squared, 1 over z times 1/2 dz, because x dx is 1/2 dz. That 1/2 is a constant multiple, and it can come outside the integral. It can also come outside the limit. So I'll pop the 1/2 all the way out. We have 1/2 lim r to infinity integral 1 to 1 plus r squared 1 over z dz. Antiderivative for 1 over z is the natural log of z. So this is 1/2 m r to infinity, natural log of the absolute value of z, evaluated from 1 to 1 plus r squared. So there's a lot of pieces here, but just write everything, change one thing per line. That's 1/2 lim r to infinity, natural log of 1 plus r squared is always positive, so I can lose the absolute values there, minus the natural log of 1 is also positive, so I can lose the absolute values there. But now we need to think a little bit, and what you may be noticing is that if you don't remember section 2.6 on limits at infinity from Calc 1 very well, you need to go back and refresh that. Because limits at infinity are all over the place here. They will also be all over the place in all the remaining sections of the course. Let's start with the natural log of 1. What is that?
Zero.
Good, yeah, that piece is 0. Now, what about the inside of the first natural log piece? As r goes to infinity, what does 1 plus r squared go to?
Infinity?
Good. So this looks like the natural log of infinity minus 0. What is the natural log of infinity? Or what does the natural log function do as its inside goes to infinity?
Doesn't it go towards negative infinity?
As the inside of the natural log goes to 0, the natural log goes to negative infinity.
Okay.
So here's what the graph of the natural log function looks like. This is the point 1, comma 0. Over here we have the point e, comma 1. And as you go to 0 from the left, he dives down like this. But as you go off to the right here, what happens?
Does it approach E?
It looks like it has a horizontal asymptote, but it doesn't. So check this out. Here's the graph y equals ln x. But if I rescale, check this out. He doesn't actually have any horizontal asymptote. If you keep going over, he keeps going up and up and up without bound. So while it might look like the natural log function has some sort of horizontal asymptote, it doesn't. It just grows incredibly slowly. I can rescale again. And you'll see if I go out far enough, he just keeps going up. So the natural log function, as its inside goes to infinity, also goes to infinity. So this is 1/2 times infinity, which is still infinity. This is something you want to remember, that the natural log of infinity is infinity. So what would I say about the integral here? Does this integral converge?
No, it doesn't.
It's divergent.
Good, very good. Yeah, good use of the language. So the integral, it is a type 1 improper integral. The integral is 0 to infinity x over x squared plus 1 dx diverges. Or you could say is divergent. And that's it. So the broad question with all of these convergence things is, does the thing converge or does the thing diverge? If the thing does converge, then we would want to try to find its value, if we can. And in section 7.8, oftentimes we can. But as we move forwards through this, we're going to have to let go of finding the value. That's going to become harder and harder, and it's going to become too hard for us to do at some point. But for now, we can usually do both. We can usually say whether the thing converges or diverges, and in the event that it does converge, we can usually state its value. If the thing diverges, then it doesn't have a value. So you don't need to worry about that. So in this case, we would just say this integral diverges, and that's it, we're done. Questions on this problem? I don't fully understand the question, Nick. Could I ask you to rephrase it? Answer these problems, both these questions. So in order to conclude that the integral is divergent, we need to show that this limit either doesn't exist or is infinity. So you have to compute the limit, or you have to get to a place where you can say something about the limit in order to conclude that the integral diverges. The answer here is just the word divergent, but we wouldn't know that without computing the limit. Does that answer your question? Okay, cool. Questions about type 1 integrals in general? Do you feel like I could give you any other problem that kind of looks like this and you would know what to do? We would begin by rewriting this as a limit and then do whatever we could do to solve this integral. After you solve this integral, you take the limit of the resulting expression. So right here, at this step, I've solved the integral. Right? And we evaluate between bounds, and that gives us some function of r. And then I take the limit as r goes to infinity and write down the answer. Either the integral converges and its value is blank, or the integral diverges. So any questions about kind of the overall strategy or how you would attack other problems of this nature? The integral is type 1 because the region whose area is being measured here is infinite in length rather than being infinite in height. So I'm glad you asked. Let me find a clean sheet of paper here, at least a bit that is clean. So check it out. The picture for this problem looks like this. Anybody know what the graph x over x squared plus 1 looks like? It has it's a fairly famous graph. It's called a witch. It's actually the graph I drew inspiration from when I made that picture there at the start of class. It looks like this on the left and like this on the right. So the integral here is type 1 because I'm trying to integrate from 0 to infinity. So the region whose area is being measured is this region, and it goes on and on and on forever in width. So this is type 1 because the region is infinitely wide. And in general, an integral is type 1 if the region is infinitely wide or infinitely long, and it's type 2 if the region is infinitely tall or infinitely high. In other words, type 1 integrals go from some number out to infinity, or from negative infinity out to some number. And type 2 integrals go from just some number to some number, but the function has an infinite discontinuity somewhere in there. So the next example I'm going to do is a type 2 problem. Let's look at it, and then we can contrast them. Before I do a type 2 integral, I need to show you how they're done. I need to show you how we set them up. So the problem in a type 1 integral is that delta x is infinity. The problem in type 2 integrals is a little different. So the graph I'm drawing here is 1 over x minus 1. 1 over 1 minus x, I guess, which will become important later. So maybe I want to integrate f of x from 1, well, let's do from 1 to 2. We'll say this is 1 over x minus 2, and 1 over 2 minus x. Doesn't matter. For you, it's just f of x. So here's 1, and here's 2. And I want to do the integral from 1 to 2. You see the problem, right? This region is infinitely tall. Goes all the way up here. So whereas type 1 integrals measure the area of a region that's infinitely wide, type 2 integrals measure the area of a region that's infinitely tall. The attack here is similar, but it's not exactly the same. Again, what I want to do is write my integral as a limit of finite integrals. So this time, instead of writing lim r to infinity, I'm going to write this as the limit as r goes to 2 of the integral 1 to r f of x dx. So here my function has an infinite discontinuity at 2, at the upper bound. So instead of trying to get that all at once, I will integrate from 1 to r, and then let r slowly sneak up on 2. So I'll push this vertical line to the right. I start by finding a formula for the area from 1 to r, and then after I've found that formula, I take the limit as r goes to 2. But you'll notice here that this should be a one-sided limit. I don't care about what happens as r approaches 2 from the right. I just care about what happens as r approaches 2 from the left. So this is limit r to 2 minus f of x dx. And that's how you set up the type 2 integrals. In general, if f of x has an infinite discontinuity at x equals c, then the integral from a to c of f of x dx is defined to be the limit as r approaches c from the left of the integral a to r f of x dx. And if we were integrating from the other side over, if I wanted to do the integral from c to a of f of x dx, I would say that that is the limit as r approaches c from the right of the integral r to a f of x dx. So this is the official way of setting up a type 2 integral. Type 2 are a little bit more complicated to set up, but it's just not any harder to work with. You just have to think a little bit more about the picture. So let's do one.
Would it be best to graph the integral before trying to solve it?
I would say yes. I would say for all of these problems, especially type 2 integrals, better to draw the graph. Better to draw the graph before doing anything else. When I was an undergraduate, one of the things that math nerds liked to do were integration competitions. And I remember once going to an integration competition at Santa Fe. I was not a Santa Fe student. I lived down in South Florida, but I was driven all the way up here by my math professor to participate in an integral competition at Santa Fe. And one of the problems was a type 2 integral. And I remember afterwards going, oh yeah, this problem was so easy. I couldn't believe it was even on the test. And he was like, well, did you notice that it's an improper integral? And I went, fuck. Because it's not immediately obvious looking at these that they're improper.
Can we go back to the other paper? I didn't get to completely write it down.
Yeah, I'll leave this here for just a second. So if you look at the objects over here, there's nothing that really gives away that this is improper. There's no infinity symbols anywhere. You have to pay attention to the function f of x. You have to know what its graph looks like to even realize that these are improper, that they require special treatment. I'll leave this here for just a second longer. Everybody good?
Yep.
So for our first example of a type 2 integral, let's look at the integral from 0 to 1 of 1 over the square root of x dx. We should know what the graph of this function looks like. It's a power function. It's something that I teach in college algebra, but in case you've forgotten, the graph of 1 over root x looks like this. And here I want to integrate from 0 to 1, which means I'm trying to find all of this area. So that region is infinitely tall. So this is a type 2 integral. And the trick is, instead of trying to do it all at once, I integrate from r to 1, and then I let r slide to the left over to 0. So I begin by writing this as limit r goes to 0 from the right, integral r to 1 over the square root of x dx. 1 over root x is x to the negative 1/2, so this is limit r to 0 plus integral r to 1 x to the negative 1/2 dx. And the antiderivative step here isn't hard, it's a power rule thing. So I get lim r to 0 plus, if I add 1 to negative 1/2, I get positive 1/2. So that's 2 times x to the positive 1/2, right? Just dividing by 1/2 is the same as multiplying by 2. And I evaluate this from r to 1. So that's lim r to 0 plus 2 square roots of 1 minus 2 square roots of r. So as r goes to 0 from the right, the square root of r goes where? What does this piece do?
It approaches 0.
Good, right? We all remember the graph of the square root function. As your input goes to 0 from the right, the square root function definitely goes to 0. So this is 2 times the square root of 1, which is 1, minus 2 times the square root of 0, which is 0. So this is 2 minus 0, or just 2. So what would I say about this integral with respect to convergence?
It converges.
Very good. So let's say thus the integral 0 to 1 over root x dx converges, and its value is 2. That's it. Not too bad, right? Okay, we got a few minutes left. So we can do one more type 2 integral, I think. First, any questions on this fella?
So when okay, so how did you go from the 2 root r to 0?
So I'm thinking about the graph y equals square root of r. So this is my r axis. This is y equals square root r. The graph of the square root function looks like this.
Mm-hmm.
So as r goes to 0 from the right, I'm thinking about a little guy walking along this graph, going closer and closer to 0. His y value will eventually go to 0.
Gotcha.
So this piece goes to 0 as r goes to 0. All those kind of pain in the ass limit problems from the first few weeks of Calc 1, they coming back. They're coming back hard here. Other questions? Or comments? Okay, let's do one more. This is a good excuse for me to remind you guys what some of these graphs look like too. Let's do the integral from -8 to 0 of 1 over x to the 1/3 dx, 1 over the cube root of x. Now the bottom of that function is 0 when x is equal to 0, so you can deduce that there's an infinite discontinuity at 0. Or ideally, you'll remember the graph of 1 over x to the 1/3. That's 1 over the cube root of x. That graph looks like this. Over here. And like this. Over here. So we've got this vertical asymptote at 0. That's the important part. And what I want to do is integrate from -8 all the way up to 0. So I'm trying to find all of this area, which definitely goes down and down forever here. So this is a type 2 integral, because I have an infinite discontinuity here at 0. So instead of trying to do the whole integral at once, I'm going to integrate from -8 to r, and then let r sneak up on 0 from the left. So I rewrite this as lim r to 0 minus integral -8 to r, and 1 over x to the 1/3, that's x to the -1/3. So then I take my antiderivative. I still have my limit up front. Antiderivative for x to the -1/3, we add 1 to the power, divide by the new power. -1/3 plus 1 is 2/3. So I'll have x to the 2/3, and then I need to divide by 2/3. That's the same as multiplying by 3/2. So that's my antiderivative. I can pop the 3/2 all the way out. It is a constant multiple. And I get lim r to 0 minus. Oh, shit, sorry. This upper bound here is an r. Sorry. That's the whole game, right? I fucked up there. I'm sorry. Yeah, make sure you go back and write this upper bound as an r. Then I'll have r to the 2/3 minus -8 to the 2/3. And the graph of r to the 2/3 is this cusp. So as I approach 0 from the left, this piece is going to 0. So I get 3/2 0 minus negative 8 to the 2/3, because the limit as r goes to 0 from the left of r to the 2/3 is 0. And then from here, it's just a matter of simplifying this expression. So I have negative, and then the cube root of negative 8 squared. That's what 8 to the 2/3 is. You take the cube root and square it. That's what the 2/3 power does. So the cube root of negative 8 is negative 2. Negative 2 squared is positive 4. So this is 3/2 times the negative of positive 4, which is negative 6. So the important part is being able to know that this guy goes to 0 as r goes to 0 from the left. And that comes from knowing this graph. Or if you want to be sloppy about it, you just plug 0 in and say 0 raised to the 2/3 is 0, right? 0 raised to any positive power is 0. The more general result there is that lim r to 0, r to the p is 0 for any p greater than 0. One-sided limits, no different. So I would say that this integral converges. And also, its value is negative 6. And I want you to take a second to appreciate just kind of how mind-blowing that is. This region is infinitely tall, but somehow it has a finite area. That's fucking weird. There's something special about that. You take any infinitely tall rectangle, its area will automatically be infinite. There's something very special about the shape of this region, defined by that curve. It gets really, really, really narrow here. Even though it goes down forever, it must get insanely narrow in order for it to have a finite area. And that's the sort of conceptual challenge that we're going to be grappling with over the remainder of this course, at least in the middle third here, this most difficult chunk, where you have things that kind of are counterintuitive. We're going to deal with solids that are infinitely long but have finite volume. Even solids that have finite volume but infinite surface area. We're going to begin by dealing with things like this, right? Regions whose length or height is infinite, but whose area is sometimes finite, sometimes infinite. We'll be talking about infinite sums, where you can add up infinitely many numbers and get out a finite number. Those are called infinite series. And eventually, we'll be talking about infinitely long polynomials that converge to finite functions. That is also a little bit mind-blowing. So the concepts here get quite heady. And the trick is twofold. On the one hand, trust the mathematics. You need to know the definitions. You can't bullshit your way through this. On the other hand, you want to start to develop some intuition. How is it possible that an infinitely long region could have finite area? Well, if it's infinitely long, it better be really fucking short. Not just some fixed constant short value, because even if you had some fixed constant shortness, if you're infinitely long, you have infinite area. So you would have to have something that gets infinitely short. Or like here, if you're going to be infinitely long, you must get infinitely narrow in order to have finite area. And that's what happened here. This region, while it is infinitely tall, gets arbitrarily narrow. As you go further down, he gets narrower and narrower and narrower. He gets narrower and narrower fast enough that even though he's infinitely tall, the area is still finite. These sort of things can be hard to wrap your head around. This section, section 7.8, is the place where it is easiest. It will get much harder from here. So invest some very real time in section 7.8. Try not just to solve these problems, but to really understand them. And that will make your life considerably easier as we move into sequences and series. I think that's all we have time for today. I'll be getting your 7.8 homework up in the next few minutes. And then on Friday, I'll show you how to deal with type 1 and type 2 integrals mixed together, or how to deal with type 2 integrals that have problems in the middle rather than at the end point, or type 1 integrals that go from negative infinity to positive infinity, all that good stuff. And also we will develop some theorems to help us detect without computation when these integrals might converge or diverge. So sometimes we won't be able to compute them. And that will be our first step on the way to developing convergence tests for infinite series, which is what we'll start talking about next week. Any questions for me in parting here as we leave? I know everybody wants their tests back. My rule is always give me 1 week. Right now I'm dealing with this problem on my work computer, so it might end up taking a little bit longer than that, but I'm hoping to resolve that problem today. As I grade the test, you'll see the grades showing up. I'm just going to go through and grade them using the Canvas speed grader. My drawing tablet that I'm supposed to be able to use to annotate your work is a piece of shit, so Santa Fe's technology kind of sucks. But we're doing our best. You'll see most of those comments being typed as a result of the shitty drawing tablet. But I promise you, you will get comments and you will get grades within the next week. If you have any other questions or anything else you want to talk about, you can always hit me up in email, Canvas messages, or come by an office hour. I should have my normal office hour this afternoon from 3:30 to 4:30. Otherwise, I will see you guys on Friday. All right. Thank you, Pablo. Thank you. That's very.
Thank you so much, Professor. I hope you have a great day. And yeah, congrats on the pregnancy, man.
Thanks. Yep. Hope you guys have a good day too. I'll see you either in office hours or in our next class. Take care.